Hello, and welcome to this video about finding the arc length of a curve defined parametrically. In this lesson, you will learn how you can use integration to calculate the length of a curve given in parametric form. In order to understand where the formula for arc length comes from, consider this blue curve. Let's let it be defined parametrically as x equals f of t, y equals g of t, and say we are interested in finding the length of the arc from t equals a to t equals b along this blue curve. Well, if we calculated the ordered pairs for the point at t equals a and at t equals b, we would then be able to form this right triangle. We'll call the base of the right triangle delta x sub 1. We'll call the height of the triangle delta y sub 1, and by the Pythagorean theorem, we would have the hypotenuse would be the square root of delta x sub 1 squared plus delta y sub 1 squared. You can see that this red hypotenuse is an under approximation for the actual length that I'm trying to calculate. To improve our approximation and reduce our error, we could find a new point in between t equals a and t equals b, which I've highlighted here in blue. We'll locate it in such a way that when we form the right triangles, the base of the first right triangle, delta x sub 1, and the base of the second right triangle, delta x sub 2, are of equal length. Now you'll notice the delta y's are not of equal length, and that's okay. We would then calculate the hypotenuse of the first right triangle, drawn here in red, and then calculate the hypotenuse of the second right triangle, drawn here in orange, and then add them together. We would have improved our approximation, though you can see we still have some margin of error between the orange hypotenuse and the blue curve. We could also have a very small, very small amount of error between the red hypotenuse and the blue curve. To further improve our approximation, we could split each of those, again, going from 2 right triangles to 4 right triangles. And now, all my bases from delta x sub 1 all the way through delta x sub 4 would be of equal lengths. When we calculate each of the 4 hypotenuses, the red, the orange, the green, and the pink, and add them together, you can see how closely that resembles the actual curve, the path we're following from t equals a to t equals b. Our margin of error would be very small, and this would probably be a sufficient approximation for most things that people would need to calculate. But still, what if we wanted to find the exact length? Well, we would have to take our approximation, which is the sum of all of our hypotenuses as I goes from 1 to n. We'd have to ratchet up the value of n all the way up to infinity. Now what that's going to do in turn is make each hypotenuse get infinitesimally small. So we'd be adding up an infinite number of infinitesimally small things. Well, when we do that, that's where we replace sigma with the definite integral. Remember, this symbol is a stretched out s, which stands for sum or summation. Now my limits are the values of the parameter t equals a to t equals b. Delta x sub I that approaches 0 becomes dx. This is just a little reminder over here that dx by definition is a delta x that's approaching 0. And each height of each individual triangle, delta y sub I, would also approach 0, so that would become dy. So we would have the integral from a to b of the square root of dx squared plus dy squared. But you'll notice no differential at the end. So what we're going to do is we're going to multiply that by dt over dt. But what I want to do is I want to take the dt in the denominator and move it into the square root. So what I'm going to do is I'm going to replace the denominator dt with the square root of dt squared. So this moves out, this moves in. Now, because this is underneath the square root and this is underneath the square root, what I can do is take the dt squared and distribute it across that square root, across the radicand. And this gives me my actual formula that uses integration, therefore has zero error, in order to find the length of a curve defined parametrically. You'll want to write this down. You want to box it in and put several stars around it, because this is the formula that we're going to use for the rest of the video. The arc length is the definite integral from a to b of the square root of the quantity, dx dt squared plus dy dt squared, with respect to t. A and b, just remember, are values of t, the parameter. They're not values of x. Something else that I think is pretty fascinating before we take a look at an example. If I rewrite that formula down here, that's boxed in here, if I rewrite it down here in green, if instead of multiplying by dt over dt and bringing in the denominator dt, if we had instead multiplied by dx over dx, that's like changing all these dt's into dx's. And instead of these being the value of the parameter, if they were now values along the x-axis, what we'd end up with is this formula, which is our arc length formula from before for non-parametrically defined curves, or just regular functions. Dx over dx squared would just be 1. Dy over dx could be written as f prime of x squared, and the dx stays the dx. So our old arc length formula for regular functions is the integral from a to b of the square root of the quantity 1 plus f prime of x squared dx. So I have two examples for us to consider. The first example is very simple. I have a parametric graph. X equals 3t plus 5, y equals 7 minus 2t on the interval as t goes from -1 to 3. And we want to find this arc length. Well, when you look at the graph, you'll notice that these parametric equations form a linear graph. If I plug -1 in for my values of t in both the x and the y equation, I'll get the ordered pairs, well, the ordered pair 2, 9. And if I plug 3 in for the t's, I'll get 14, 1. Now, because this is a linear graph, I could calculate the arc length by simply doing the Pythagorean theorem. I just need to know how big each leg is. Well, if this y-coordinate's 9, and we drop down here on level with this y-coordinate, which was 1, that makes the height of this triangle 8. So this leg is 8. This x-coordinate's 2, because it comes from this coordinate. This x-coordinate is 14. That makes the base 12. So c squared equals 8 squared plus 12 squared. So c, my hypotenuse, which is my arc length, would be 4 square roots of 13. If I apply the arc length formula from the previous page, the arc length would equal the integral from a to b, and again, those are values of the parameters, so from -1 to 3, of the square root of dx dt squared. Well, if I take the derivative of 3t plus 5, I get 3 squared. And if I take the derivative of y, I get -2. So I put that here, and I need to square it. And I need to integrate the square root of this with respect to t. Well, 3 squared is 9, -2 squared is 4. Added together gives me 13. And when I integrate the square root of 13 with respect to t, I get square root of 13t. And now I'm evaluating that from -1 to 3. Plugging in 3 first, subtracting what I get when I plug in -1. 3 minus -1 is 4, so I get 4 square roots of 13, which confirms the answer that we had from before when we just did it with regular Pythagorean theorem. Now, if all parametric graphs were always linear, then we really wouldn't need this formula. We could always just do it by Pythagorean theorem. However, most parametric equations are going to give you a curved path rather than a straight path. So for our final example, let's consider a trajectory problem. Say we had a ball that was thrown at a 24-degree angle of inclination from a height of 1 meter with an initial velocity of 20 meters per second. Find the arc length of the trajectory. So what we really want to find is, if we release the ball here and we actually measured the distance the ball travels in the air, how far is that? what's the length of the path that the ball takes? Well, the first thing we'd have to do is write our parametric equations. Quick reminder from pre-calculus. X is equal to v naught cosine theta t. V naught is my initial velocity, in this case 20 meters per second, times cosine of my initial angle of inclination, which was 24 degrees, times t. Y is equal to 1/2 gt squared, and g is the acceleration due to gravity, so it's negative 4.9 t squared, plus v naught sine theta t, so again 20 sine of 24 degrees t, plus our initial height, which is 1. Next, we could graph that on a calculator and find when the ball lands. Now, the ball lands when the y-coordinate is 0. So if I plug 0 in here and solve this for t by using the quadratic formula, you'll get t to be about 1.775. That means from the time we release the ball at time 0, the ball is in the air for 1.775 seconds, because that's the time that the ball lands. Well, here's my arc length formula. It's the integral from a to b, and my parameter in this case is t, my time in seconds. So 0 to, here I stretched out my value of t for accuracy, 1.775, blah, blah, blah. Know that really there would be air resistance, so it really wouldn't be as accurate as I'm claiming anyhow. And then the rest of the arc length formula is the square root of dx dt squared plus dy dt squared. Just note that I know you're used to the derivative of cosine being negative sine, but this is cosine of a constant. So we're not actually taking the derivative of cosine, we're taking the derivative of some coefficient times t to the first, which would just give us the coefficient. So the derivative of 20 cosine of 24 degrees t is just 20 cosine of 24 degrees without the t on it. Now remember, we need to square dx dt, plus dy dt, well, the derivative of negative 4.9 t squared is negative 9.8 t. And similar to what we did before, the derivative of 20 sine of 24 degrees t is just the coefficient, which is 20 sine of 24 degrees. And we're going to square dy dt. And then here's our differential at the end, dt. When we type that into a calculator, we get 33.633, and that would be measured in meters. So 33.633 meters is the arc length, or the length that the ball would actually go through the air along this path. Just for the record, it's only a little further than the actual distance along the ground. The distance along the ground is just a little over 32, and we got for our arc length 33.633 meters. So that's it. It's actually pretty simple. Remember, the arc length formula for a parametrically defined curve is the integral from a to b, and those are values of the parameter of the square root of dx dt squared plus dy dt squared dt. That's everything. I'm Murray Wright. Thanks for watching. Bye.